Here's part 2 of the IIR examples. It follows from the video you hopefully just watched. In this example, I'm looking at a particular case of an RC filter, and this might be a case where we have a particular RC filter that we're trying to mimic. This is a low pass, and the values of the resistor are this, 1,000 ohms, and the capacitor has this capacitance. And the question is, and we furthermore in this case say that the digital system that we are working with has a sampling frequency which is set already. Then we can ask the question, what is omega c, and how do we kind of translate this? So this is like the second case I talked about. It is not general. We're trying to match a particular filter that has a pole. Okay. So what we can do first of all is you say, well, for this kind of RC filter, what's the cutoff frequency? 1 over RC, and you plug in this times this, 1 over, gives you 1,000, which means the frequency is actually 1,000 divided by 2 pi in hertz. But we're working in this omega, which is 2 pi times frequency, so it's 1,000. Now, okay, then we have this frequency warping equation. This is the generic equation. In this particular case, we know the sampling frequency, so that determines T. We know the resistor and capacitor values, so that sets this. So we basically are going to solve for this, for the digital frequency. So we can say, okay, this is the general case, but let's say that's the cutoff. This is going to be 1,000. It's basically 1,000 equals 2 over t, but t is 1 over the sampling rate, so we can say this is 2 times 3,000, 6,000, tangent omega c divided by 2. So then from that you can solve, and I won't do it, but you can say omega c equals 2 times a tan of 1/6. All right, and then if we want to complete the process, we can plug in S equals 2 over t, but again that's going to be 6,000 is 2 over t in this particular case, times 1 minus z inverse, 1 plus z inverse, and then we would have an h of z. And the cutoff frequency for this, if we were to plot it, would be, we'd see something that would kind of roll along, go like this, and the cutoff frequency here would be the omega c we calculated above. Okay, so those 3 examples I showed you are examples of doing things by hand, which is useful for taking an exam, for example. But in general, you would be doing filter design using some design tool, whether it's MATLAB or Python or who knows what. Okay, and so in MATLAB, the syntax that you used before is you could basically say, if you want a Butterworth filter, say the filter order, say the normalized cutoff frequency, some number, so pi would be 1, so 0.2 pi would be 0.2, and it gives you your filter coefficients you can then use to actually do the filtering. Okay, so this is great. You use this in the MATLAB project, and one question is, how do you pick n? And the answer to that is there's another command you can do, which is called butterord, that'll figure out for a Butterworth filter what n you should use. Okay, so then the question is, well, what is that doing? So that's what we'll look at now. Okay, so what the butterord command and similar commands are doing is they're implementing a bunch of design formulas that are in the textbook or similar textbooks, and you can find them in actually some of the homework problems in the Proikis and Manolakis chapter go through using those formulas. And to solve these, you need to know more about the particular forms of the different filters. So a Butterworth filter was analyzed by Mr. Butterworth, and he figured out that it is a kind of the form of this, where you have h, here we're looking on the frequency axis, so this is, in general it would be h of s, but we're looking on the frequency axis, so we have some big omega, is 1 over 1 plus this thing to the 2n. So you have the frequency divided by the cutoff frequency raised to the power 2n. And here omega c is the minus 3 dB point. I should say n is the filter order. So this is a, let me see, I'll say n equals filter order. And okay, and that's one way. This specifies it. So it basically says, if you know your frequency, if you know the filter order, and if you know the cutoff frequency, then you can calculate the magnitude. Okay, it turns out that Butterworth filters look something like this. They have a bunch of poles on the in H of S. This is the S transform. They have a bunch of poles on a circle like this, and there'll be one pole for every filter order. So you basically count the poles. Now, alternatively, you can rewrite this, which turns out to be useful as this way. So you would basically say it's 1 over epsilon squared frequency divided by omega p, where this is now passband frequency. And this epsilon is just basically when you have the frequency equal to, I'm having some pen difficulties, frequency equal to the passband frequency here, this goes to 1, and the it doesn't matter what the filter order is, it's 1 to some power. So 1 over epsilon squared is the magnitude at the passband frequency. It's just another way of specifying your cutoff. This is for, I'm assuming here, a low-pass filter. Okay, so these formulas are figured out for every type of filter, all the standard filters, elliptical, Bessel, whatever filter. There's kind of corresponding equations. And the way you use them is they, let's say we wanted at some frequency, we'll call it in the stop band, so omega sub s, we wanted the attenuation to be at least as small as some delta 2. From the formula above, we can just plug in, instead of our frequency, we plug in omega sub s, and we have this is equal to delta 2 squared. Okay. So now if we could specify the attenuation we want, the attenuation at that knee, omega p and omega s, if we specify everything else, we can figure out what n has to be to meet that spec. And so this is basically when you call the commands like butterord, you're telling it all of these things, and it is using a formula to calculate what n should be to meet these.